Good morning, sir. I'm Rahul Ghosh, EC third year, and I have made this tool for an experiment of digital communication. In this experiment, I have created an interactive tool called Signal Explorer to demonstrate sampling, aliasing, and reconstruction of a signal. The purpose of this tool is to make the effect of changing the sampling frequency easy to understand visuals. Instead of only looking at the theoretical results, we can change the input values from here, and then we can change we can see the change in graphs immediately at the same time. On the left side, we have three main controls. Okay. The first control is frequency 1, which determines the frequency of the first sinusoidal component, and the second is frequency 2, which controls the second sinusoidal component. In this experiment, the second component has a lower amplitude, so its contribution to the overall waveform is smaller. The third control is the sampling frequency. This is the most important input because changing it determines whether the signal is sampled sufficiently or whether aliasing occurs. For the current setup, the two signal frequencies are 18, like here you can see, so 18, and then in the next it is 25. 5 is the highest frequency component. Then the Nyquist limit for the experiment is 50 hertz. That, that one. And the tool provides three preset conditions on the left: above Nyquist, at Nyquist, and below. I can use these buttons to quickly compare three situations. Like if I do above Nyquist, then it will look up like this. If I do at Nyquist like 50 hertz, it will be like that. And in below Nyquist, it will be like that. So now, before looking at the individual case, let me explain how the tool works internally. First, the website generates the original two-tone signal at a very high protein resolution. This gives us the smooth reference waveform showing gray. There is a reference waveform that one. It's shown in gray color, so it's little bit, I mean, not comfortable for eyes, but it is there. So the reference that that one, and the tool then creates the actual sample points according to the selected sampling frequency. So these points, and these are the red points that we can see on the time domain graph. After that, the tool uses those samples to generate a reconstructed waveform using sync interpolation. This is shown as the blue dashed curve, and that blue dashed curve is that reconstructed waveform using sync interpolation. This is shown as the blue dashed curve. So the basic process inside the tool is original signal, and then original signal to sampling in sample points, sync reconstruction, and comparison with the original signal. An important point An important point in that implementation is that the plotting resolution and the physical sampling frequency are kept separate. The graph may contain many points so the curves look smooth, but that does not mean the signal is being physically sampled at that high resolution. The actual rate sample points depend only on the sampling frequency selected on the left. Now I'll start with the first condition above Nyquist, which uses a sampling frequency of 100 Hz. Here the sampling frequency is sufficiently high compared with the highest frequency in the signal. If we look at the time domain graph, the rate sample points are relatively dense. They follow the gray reference waveform closely so the reconstruction has enough information to reproduce the original signal. The blue reconstructed curve is therefore close to gray reference curve. This is what we expect when the signal is sampled properly. Now if we look at the magnetic spectrum, we can see the frequency components of the signal. The spectrum tells us which frequencies are present and how strong these components are. For the signal, we expect the main frequency component around 18 Hz and 25 Hz. Since the signal is real valued, the spectrum also has corresponding negative frequency components. The important observation here is that the spectral copies created by the sampling may remain separated. They do not overlap with the original signal spectrum. That is why there is no significant aliasing in the case. A reconstruction error graph at the bottom shows the difference between original waveform and the reconstructed waveform. Since the reconstruction is good, in this case the error remains relatively small apart from the small numerical and boundary effects caused by the final simulation. Now I'll change the sampling condition to ethnic, which sets the sampling frequency to 50 Hz. This is exactly the limiting sampling rate for the 25 Hz component. Now we can see the rate sample points are much more widely spaced compared with the 100 Hz scale. The pattern on the sample has changed because there are fewer samples available to describe each cycle of the signal. There is also a special behavior here because of 25 Hz components is a sine wave with zero phase. At exactly 50 Hz sampling, the samples of the component fall and it's zero cosines. Now I'll select the third condition given which sets the sampling frequency to 30 Hz. This is where the most important effect of the experiment becomes visible. The sampling frequency is now too low to represent the highest frequency component correctly. If we look at the time of the rate sample, and sample points become much more separate. They no longer provide enough information to follow the rapid variations of the original wave. More importantly, the reconstructed blue waveform now has a noticeably different pattern from the original gray waveform. This is caused by aliasing. Below the Nyquist level, the sampling pattern changes significantly. Spectral overlap occurs and aliasing causes the original frequencies to appear as different frequencies. Therefore, the main observation from the experiment is the sampling frequency directly controls how much information about the original signal is captured. By changing the inputs and observing all four graphs together, we can clearly see the complete effect of sampling from the original waveform to the discrete sample, to the frequency spectrum, and finally to the quality of reconstruction. Thank you.